There are three auctions in the MakerDao stablecoin system: collateral auction, debt auction, and surplus auction. The collateral auction is called when there is a debt that is under collateralized and the collateral must be liquidated. Debt auction is called when there is some amount of unbacked debt, so the MakerDao system will sell its governance token, MKR, to repay this unbacked debt. And the surplus auction is called when there is profit inside the MakerDao system, so it will try to buy back the governance token, MKR. For the next few videos, we'll work our way through collateral auction. And to start off with, in this video, I'll rewrite the code for the liquidation engine. Inside the MakerDao system, this contract is called the dog contract. From the GitHub repo of DSS, I'm going to copy the dog contract. Inside the terminal, I'll create a new file. Let's call this liquidation engine.sol and then paste our code. And then before we start, I'll run the forge format, forge fmt. And then I'm going to remove some of the comments and then change the solidity version. Okay, let's start by renaming the interface. The Clipper-like interface is the collateral auction. So let's rename this as iCollateral auction. It has two functions, IOK and kick. IOK will represent the collateral that is being sold at this collateral auction. So let's rename this to collateral type. The function kick is called to start the collateral auction. So let's call this start. Then it takes in several inputs. Tab will be the amount of coin that must be raised from this auction. So let's call this coin amount. Lot will be the amount of collateral that is being sold. Let's call this collateral amount. And then the user will be the user that's going to receive any leftover collateral after the auction. Let's call this user. And the last input, keeper, will be the address that is going to receive DAI for starting this collateral auction. It's an incentive for users to start a collateral auction. Let's call this keeper. Okay, so that is the iCollateral auction. Moving on, we have the BAT interface. Let's rename this as I. Actually, we don't need this since we already have the ICDP engine interface defined. So I'll just remove all of this. And then up at top, let's import this. Import ICDP engine from go one above interfaces ICDP engine.sol. Okay, next we have the interface called BAO-like. BAO we'll rename this. The BAO contract will be the DES engine contract. We'll cover this in another video. Let's rename this to IDS engine. And then it has a single function called fes. What this function will do is it will add the amount of debt to a queue. More details will be covered in the video when we rewrite this DS engine. So for now, let's just call this push debt to queue. It's going to take in a single input, the amount of debt to push. Okay, and then now we have our dog contract. We'll rename this as liquidation engine. Liquidation engine. This will be the dog contract. And notice it's going to have some authorization logic. So let's say this is auth and then also import the auth contract. Import auth from go one above lib auth.sol. And then now we can remove this auth logic. Next, we have a struct called IOK. Let's rename this to collateral. And then we have several data that is stored inside this struct. The first one is called clip, and this will be the address of the collateral auction. So let's call this as auction. Next, we have chop, liquidation penalty. Let's just call this penalty. This penalty will be multiplied to the debt that must be recovered. Next, we have data called whole. Whole will be the maximum DAI that is needed to cover debt plus fees for inactive auctions per collateral. So this will represent the maximum debt that is currently being recovered by a collateral auction per collateral. So let's call this max coin. And then dirt will be the current amount of debt in a collateral auction. So let's call this coin amount. The maximum coin will set an upper limit to the amount of coin amount inside a collateral auction at the moment. Okay, and then we have the BAT-like. Let's rename this as ICDP engine. BAT will be CDP engine. Then we have a mapping from IOK. We rename this as collateral. IOKs will be collaterals. And then we have some state variables. BAO will be DES engine. BAO-like will be IDS engine. Like will be the state variable that is used to stop the contract. We'll remove this and then inherit the circuit breaker contract that we wrote. Circuit breaker. Same over here. Circuit breaker. And then inherit it over here. circuit breaker. Next, we have the state variables called whole with a capital H and dirt with a capital D. So these two state variables are similar to the state variables that we named over here. Over here, it's keeping track of the maximum DAI to be raised per collateral auction and the current amount of debt that is being raised for the auction. Over here, this will represent the total of all collaterals. So whole will be the maximum amount of DAI that is inside all active auctions. Let's rename this as max coin, and dirt will represent the current total amount of coin that is being raised in all of the auctions. Let's rename this as total coin. Okay, next we have some events. In this video, we'll just remove them. Next, we have the event called bark and digs. Let's rename this as liquidate. Bark will be the function that is called to kickstart the liquidation. And digs will be a function that will be called after a collateral auction ends. Let's call this remove. And then it has some data that is stored here. Let's call this call type. Yearn will be CDP. Ink will be delta call, delta collateral. Art will be delta debt. Do will be the amount to be raised. And clip will be the address of the collateral auction. Next, we have the event remove. IOK call type. And then rad will represent the amount that was removed, the amount of debt that was removed. Okay, let's move on to the constructor. It's going to take in the address of the back contract. Let's rename this as CDP engine. And then the bat, I'll rename it as CDP engine. Interface I CDP engine. And then I'll remove these state variables. They are handled by the auth contract and the circuit breaker contract. Next, we have some math functions. We'll just import the math library, so I'll remove all of them. And then next, it has some functions that an authorized account can call to set some of the state variables. In this video, we'll remove all of this and we'll jump right ahead to the function that is relevant to liquidation. We have a function called chop. We renamed chopped as penalty, the liquidation penalty. So let's also rename this function as penalty. IOK will be the call type, and the state variable IOKs will be collaterals. Okay, moving on. Now we have a function that will start the liquidation. Let's call this liquidate. Okay, and then for the inputs, let's rename IOK as call type. Yearn will be CDP, and keeper will be keeper. First, it checks that live is equal to 1, or live is set to true in our case. So let's add a modifier, not stopped. The modifier comes from the circuit breaker contract. Next, it's going to query the back contract for Yearn and for IOKS. Yearn, we renamed it as position. So here, let's say ICDP engine dot position memory, let's call this POS, is equal to CDP engine dot positions. For the inputs, we'll need to pass in the IOK or call type, and Yearn will be the address CDP. The two data that we're going to need is ink and art. As a reminder, ink will be the amount of collateral locked in this CDP position, collateral, and art will be the amount of debt. Okay, so now we can remove this, and we see over here that it's also querying the IOKS. So let's do this over here. So ICDP engine, collateral, memory, I'll call this C, and then the function that we need to call is called collaterals, identified by call type. Next, it's going to get the collateral information that is stored in this contract. The struct is called collateral. This time, let's call this call. Store that collaterals of call type. And looking at this code, the data that we're going to need from this collateral is rate, spot, and dust. Dust is defined over here, so we don't need this. Rate is defined over here, so we don't need this. And as a reminder, rate will be the rate accumulator, spot will be the spot price with some safety margin, and dust will be the minimum debt that must be borrowed. And now we can remove this code. And for Dart, let's come back to this later. Let's figure out what this variable should represent. Okay, and then we have require spot. Spot will come from the data from the collateral. C.spot is greater than 0. So this makes sure that the collateral is initialized. And ink will come from the position. So position POS.collateral multiplied by spot. So multiply by C.spot. And on the other side of the inequality, we have art, which will come from the position. This will be debt. So let's rename this as POS.debt. And rate will be the rate accumulator, c.rate ACC. Remove this multiplication and then multiply it here. So what it's doing here is it's making sure that the spot for the collateral is greater than 0, and it makes sure that the collateral is initialized. Next, it checks that the amount of collateral locked multiplied by the spot. This will give us the value of the collateral for this CDP position is less than the positions that multiply by the rate accumulator, which will give us the amount of DAI plus the fees that the user borrowed. This inequality checks that this CDP position is currently under collateralized. Okay, moving on. Next, it checks that whole is greater than dirt. Whole, we renamed it as max coin, and dirt, we renamed it as total coin. Milk will represent the collateral information that is stored in this contract. Whole will be max coin, and dirt will be coin amount. So it's making sure that the total amount of debt that is in all of the auctions is less than what it's set as max. And this also holds for the setting for collateral, that the debt inside the collateral auctions specified by this collateral is less than the max that is allowed for this collateral. Okay, moving on. Next, it creates a variable called room. And what it's doing is it's calculating the minimum between this max coin, total coin, and collateral max coin and collateral coin amount. So let's use this. And then I'm going to replace this inequality with a minus, same over here. And then we'll call the function math.min. And then going up, I'll import the math library, import lib math.sol. Okay, going back. This variable room will be the maximum amount of debt that can be sold for this collateral auction. Okay, and then going down. Here, we declare the variable called dart. Now it's being set. Art is position.debt. And then here it's multiplying room by WAD, dividing by rate. So this will be c.rate ACC. And then dividing by call.penalty. What's going on here is it's trying to figure out the amount of debt to be sold for the auction. The target amount of coin to raise for the auction is given by this equation. Target coin for auction is equal to the debt multiplied by the rate accumulator multiplied by penalty. Remember when we multiply debt by the rate accumulator, this will give us the amount of DAI plus the fees that the CDP owns. And then multiply this by a penalty. And that will give us the target amount of coin to raise for the auction. So from this equation, if we wanted to calculate the amount of debt to raise, you'll need to divide by rate ACC and then divide by penalty. And this will give us the debt. So this is what this part of the code is doing. So room will be equal to target coin for auction divided by rate accumulator divided by penalty. So this dart will represent delta debt, the amount of debt to be raised for the auction. Let's go rename this over here as well, delta debt. And then we'll call the function math.min. Okay, and then moving on, it has some edge case for partial liquidation. Art will be position.debt, delta debt. If position debt is greater than delta debt, this will only happen in the case when this number is less than position.debt. So in this case, we need to make sure that after the collateral auction ends, the amount of debt that is left over is greater than or equal to the minimum debt that is allowed for a CDP. So this is what this part of the code is doing. Okay, so let's rewrite this. Art will be pos.art minus dart. Dart will be delta debt. Multiply this by the rate accumulator. And this must be less than dust. Dust will be a configuration for the collateral, c.min debt. Once this delta debt is recovered from the collateral auction, the leftover will be the current debt, position.debt minus delta debt. That will be the leftover. Multiply by this by the rate accumulator. And if this is less than the minimum debt, then it's going to liquidate all of the debt inside the position. Delta debt is equal to position.debt. Otherwise, if the leftover after the collateral auction is greater than min debt, then it double checks that delta debt multiplied by the rate accumulator is greater than dust. Dust is c.min debt. Okay, moving on. This handles the case of partial liquidation. Next, it creates a variable called inc. So we said inc was the amount of collateral locked in a CDP, pos.collateral. Multiply this by dart, delta debt, the actual amount of debt that must be raised for a collateral auction. And then divide by art, the amount of debt inside a position. So it will take the amount of collateral locked in a position and then take the fraction of delta det divided by position det. If delta det is equal to position.det, then this will return a 1. So the amount of collateral to be liquidated will be all of the collateral locked in a CDP. Let's call this delta call, the amount of collateral to be sold off for the collateral auction. And then it checks that this delta call is greater than 0. And then dart delta det is less than this number, and delta call is less than this number. Next, it calls the CDP engine. CDP engine calls the function grab. And then it's passing in several inputs. The first input will be the collateral type, call type. Next input will be the CDP. The next input will be the destination where the collateral is sent. This will be the address of the collateral auction. Gem DST will be call.auction. Next input will be the det destination. This will be the det will be sent over to the valve contract, the DS engine contract. The next input will be the delta collateral, the amount of collateral to take from this CDP position, and delta det. CDP engine will grab the collateral of the CDP, send it over to the auction, and the current det will be registered over to the DS engine. Next, it will calculate the amount of coin, the amount of DAI to be raised. And it's going to multiply delta det multiplied by the rate accumulator, c.rateACC. Then it's going to call the function DS engine push det to Q. And then moving on, inside here you can see that it is calling the collateral auction. So let's rename this as I collateral auction. First, it creates a variable called tab. From what it's doing, we can guess that this is the amount of coin, the target amount of coin to be raised for the auction. Let's call this target coin amount, and it is calculated by taking do. Do represents the det multiplied by rate ACC. We multiply this by the penalty and then divide by WAD. And then it adds to dirt. Dirt will be the total coin. To total coin add target coin amount. And then also store this into the state variable collaterals for call type coin amount plus equals tab target coin amount. And then finally it calls the collateral auction. The collateral auction is stored under call.auction. Call the function kick. So tab will be coin amount, lot will be collateral amount, this will be user, and keeper will be keeper. Tab will be target coin amount, collateral amount will be stored in delta call, yearn will be CDP, keeper will be keeper. Okay, so this is how the collateral auction is started. The function will be start. We're almost done with the function liquidate. Let's rename this as liquidate. Call type, CDP, delta call, delta det, do is do, and this will be call.auction for the auction ID. Okay, so that completes the function liquidate. Let's move on. The function cage for this video, I'll just remove it. Digs. Let's rename this as remove. Actually, let's rename this as remove coin from auction. For the input, it's going to take in call type and rad, the amount of det to remove. And what it's going to do, it's going to subtract from dirt, from total coin minus equals rad. And then it also updates the coin amount inside the collateral. So let's say collaterals, call type, coin amount minus equals rad. And then emits the event remove. Okay, so that completes the function liquidation engine. Okay, let's try compiling the contract, forge, build. Okay, and then I see some errors on line 135. Remove the comma, try compiling again. Line 144, remove this parentheses. Line 154, remove this parentheses. Remove this extra .sol extension. Line 77. Okay, and our contract compiles.